Thank you. We will continue with the next presentation. It's by Justin Awaraka, and she will talk about vertical land motion of the high plain Aquifer region of the central United States.
All right. Thank you for inviting me, and thanks to my co-authors. So the motivation behind this study stems from work the Nevada Geodetic Lab has been doing for the past several years. And some of that work is summarized in this image of the contiguous United States and parts of North America. Red is uplift, blue is subsidence. And some notable signals shown include post-glacial rebound in Canada and the four bulge collapse signal in the United States. You can see regional uplift from magmatism and post-seismic and interseismic signals. And then there's also regional subsidence from water removal and oil and gas and aquifer depletion as well. So GPS imaging can also be used to discover previously unknown signals and investigate the cause of the motion, such as this one in the central United States that is in contrast to the downward four bulge collapse signal. There's no known tectonic activity great enough to cause post-seismic rebound, which is generally 6.5 magnitude or greater. There's no known magnetism in this area, but it does include the High Plains Aquifer, so maybe they're related. So some background on the High Plains Aquifer. It's the largest aquifer in the United States. It's a major source of groundwater for crops and livestock. And the groundwater is stored in unconsolidated sediments in an unconfined aquifer. And groundwater levels have declined in the last 100 years, in particular in the southwest part of Kansas and the Texas Panhandle, which has water levels have declined in some places by more than 45 meters. And estimates by Scanlon et al. Estimate that 330 cubic kilometers of water has been lost between 1950 and 2007, and that the groundwater mass loss rate is approximately 5.7 cubic kilometers per year. So we want to know, is aquifer depletion causing high plains crustal uplift? To help answer this question, we used several different data types to investigate vertical land motion in the Great Plains region and its relation to the High Plains Aquifer. So we divide the High Plains into northern and southern sections because their signals are very different. We create uplift maps based on GPS data. We compare trends in water equivalent height from GRACE. We look at climate trends using Palmer Drought Severity Index data as an analog for wet and dry seasons. And then we use well data as an indicator of the human impact on the aquifer. And unfortunately, there's not enough time for every part of our study, but we were published earlier this year, and you can definitely look at that in more detail. So to start with, we use GPS imaging to analyze vertical land motion on the High Plains Aquifer. And we do that by plotting velocities at each station, estimated by MIDAS, which gives us velocities and trends rather that are insensitive to outliers, seasonality, and undocumented steps. Next, we apply weighted median spatial filtering to remove speckle noise, like you can see kind of in Oklahoma and parts of the Texas Panhandle. Then we interpolate these velocities to a grid using weighted median estimation to create a vertical velocity field. Signals similar between stations are enhanced by GPS imaging and may be ascribed to the spatially coherent movement of the solid Earth. And unfortunately, there can be some artifacts which appear as weird fingers or shard-like features associated with the non-homogeneous GPS station distribution. So to correct for that, we use a bootstrapping statistical analysis and take the median value of the vertical rate at each pixel to create this velocity field. We then solve for common signal by removing the four bulge collapse modeled by the ICE 6GD model we remove it from our GPS imaging result. And that gives us this image on the far right that shows 1.7 millimeters per year of uplift at the peak, located approximately on the Texas Panhandle and extending throughout most of the southern High Plains aquifer. So to understand the hydrological impacts on vertical land motion, we use GRACE data, which measures gravity perturbations, including the changing distribution of water mass on the Earth's surface, including groundwater extraction. And what this figure here really does is it emphasizes the difference between the north and south aquifer. In the northern aquifer, there's an increase in mass. In the southern, there's a decrease in mass, and the area of greatest mass loss is centralized around the Texas Panhandle, where we're seeing GPS uplift and where we've seen greatest groundwater decline. So next, we wanted to take a deeper dive into signals specifically located in the aquifer bounds. So we gathered 28 GPS, 28 GRACE MassCon 16 PDSI time series that intersected or were within the High Plains aquifer bounds to identify overall trends. For the northern aquifer, we see more frequent periods of extreme wetness. We see cyclical water mass loss and recovery, and there are more periods of mass gain than mass loss. And the general trend shown in GPS shows subsidence. For the southern High Plains aquifer, we use 49 GPS, 30 GRACE, and 12 PDSI for data within or intersecting the High Plains aquifer. And the trends in the southern aquifer indicate there are more frequent periods of extreme drought, greater mass loss with little to no recovery, and the general trend for GPS shows uplift through 2014, which is the end of Texas's worst drought in state history. And then after 2014, there's gradual leveling. So we wanted to know how much water would have to be removed to cause the uplift signal that we're seeing. So we developed a very simplified unloading model using the load-def software to estimate the freshwater mass unloading rate. And the perimeter of the mass unload is based on a simplified region of vertical velocities with a rate greater than 1 millimeter per year. So we solved for water load thickness that minimizes the misfit between the observed uplift rate on the far left and that predicted by the model in the middle. And even though it's simplified, our model shows that a loss of about 11 centimeters per year centralized on the Texas Panhandle can approximate the uplift signals shown by our GPS imaging result, which is equivalent to about 5.1 cubic kilometers per year of water volume loss, which is not so different from the range given by Scanlon and given by GRACE, which was 6.7 cubic kilometers per year. So to summarize this brief presentation, we've shown that GPS signal characteristics, comparisons with other data, and modeling indicate uplift of the High Plains aquifer is from elastic hydrological unloading. The correlation of signals with well-level decline suggests uplift is at least partially, and I would say probably largely anthropogenic from groundwater depletion of the aquifer. And finally, we do not see subsidence signal typically associated with aquifer compaction during depletion because this aquifer is confined. Thank you.
We have time for questions. Manu?
Great presentation regarding the last conclusion that you made. You apply a median filter and any localized subsidence should have been removed. Have you tested, have you investigated that actually you are not removing subsidence due to aquifer compaction?
That's a really good question. Part of the reason that we may not be seeing that type of like a localized compaction signal is the resolution of our GPS is probably not as small as it needs to be. If I had a lot more stations in the area, we might be able to test that a little better. But at this resolution, we have about 2 degrees because there just aren't enough stations located, in my opinion, in this area. But we haven't been able to investigate that based on the resolution.
Thanks.
And Justin, we have a question from online audience. The question is there a ground deformation signal in the southern part of your study area due to petroleum or natural gas extraction from the Permian Basin?
Yes, this is something we actually investigated. And the Anadarko Basin is located on the Texas Panhandle, and the Permian Basin kind of at the southern end of our aquifer signal. The quantity of oil extracted in the history of oil extraction that I could find was much smaller than the amount of water extracted. So it's like Scanlon said 330 cubic kilometers. Some of the estimates I saw were like 15. So it might have a very small effect, but the signal is largely going to be dominated by the water extraction.
Thank you.